Hello and welcome to the first lecture, one of the first lectures for the machine learning series. In this lecture, we're going to do a quick review of very basic calculus concepts such as integration and differentiation. So I'm Professor Wu, and let's get started. So functions. Hopefully by now, at this point, you've dealt with functions in your previous classes. In machine learning, we very often use different functions to describe various natural phenomena. And these functions, you can think of it as you have a function. What you do is you put some value inside the function, and the function spits out some kind of result. So you put x in, you get y out. So that's not a foreign concept to you, hopefully. And here's an example of a function, a very, very simple one, where you put some x in and you will get some output. And this function can be shown as a green line here. So you put some value in, like 0, right? If you put 0 in, if you put 0 here, that will be 0, and then you got 0.2. So this line basically tells you that given some input you put in, what the output would be. Okay, so a function can be visualized as a system where you put some input in and get some output out, and you can plot that on a graph. So that's basically what a function is. Now, with functions in machine learning, we very often want to know where the function is going. And when I say going, what I mean is that as the value of x increases, is the function going up? Is the function going down? Or is the function going nowhere? Okay, so this directionality of going up or down is a really, really big deal in machine learning. And we're going to see why pretty soon, right? So as the value of x increases, will the function go up or down? The derivative of a function, also known as a slope. Derivative of a function give us essentially this information. How does it give us the information? Well, if we calculate the derivative at a certain point, and the derivative happens to be positive, that means from that point, as you increase x, the function is going up. That's if the derivative is positive. Now, if the derivative is negative, it means from this point, the function is going to start going down, right? So as x increases, the function goes down. So the derivative of a function essentially tells us at any given point whether the function at that point is starting to go up or starting to go down. Okay? And the magnitude of the derivative, so if it's a large positive number, then it's going to go up very sharply. If it's a small positive number, it means it's going to go up very slowly. Similarly, if it's a small negative number, it means it's going down very slowly. And if it's a large negative number, it means it's going down very quickly. So the magnitude of the slope tells you how quickly it's going up or down. And obviously, 0, right, means it's not going up or down, it's just going flat. Okay, so we can calculate the derivative and the slope. So given a function, we can calculate the derivative and the slope at any given point, and we symbolically represent that by writing this. So this right here means we're taking the derivative of this function, right, at dx. So with x as the variable. So that's one way to write it. Another way is to write f prime. So this little prime means this is no longer the function f anymore. This is the function, the derivative. So when we plug x in, it's going to tell us that at this point, x is the function going up or down. So here's a quick example. That green line we were just looking at has this equation, right? 0.3 plus 0.2. Now, if we take the derivative, derivative of this function, then then let's say the derivative of function is another function, like 0.6. Now, how do we get this? Like that's what we're going to do today. But the point is, once you have the derivative, you can plug any value into the function and it will tell you. So for example, over here, 1, obviously, if you plug 1 in here, right, you plug 1, it'll be 0.6 times 1 because this is the equation. So 0.6 times 1 is just 0.6. So we know that this point is has a derivative of 0.6. Okay, it's positive, means that at this point, we know that the function is going up as x increases. Okay, and its magnitude is 0.6. What does that mean? It means that if you increase x by 1, you're going to increase y by 0.6. So you can see, assuming the slope doesn't change, given the same slope, given the same derivative, right? When you increase the x by 1 from 1 to 2, notice how the increase is 0.6 because over here 0.5, 0.6 give us this point 1.1. So that's what this means. Like it's positive means it's going up, the function is going up, and it's going up at a speed of 0.6. So that's what a derivative is kind of telling us. Okay? So over here, notice how at this point, it's not going up or down. Like the derivative here is 0. So you can expect that if we plug 0 here, right, then we're going to get 0 slope. Means at this point, the function is not going up or down. So looking at this plot, you can kind of understand that and distinguish the concept of a function, which green line is a function. And then from the function, you can calculate the derivative. And then with the derivative, it tells you that given any point in the function, is the function going up or down? Okay, so distinguish the function and the derivative of the function. Now, functions, right, doesn't necessarily only have one input. Sometimes you can have multiple inputs. So in this particular example, let's say we have 3 inputs, x1, x2, x3. Okay, and then it gives one output. So if we have x1, 2, 3, then we will have to input 3 numbers into the function. So for example, let's say we put 1, 0, 1. Okay, therefore it's 1, 0, 1. So this will become -3, 0, 1, which give us -2. So you see, this is an example where we have 3 input. Now, we were just talking about derivatives of single input. So what will happen when we have derivative of multiple input? Well, when we have multiple input, then the derivative has to match the number of input because we need to know that as x1 increases, is the function going up or down? As x2 increases, is the function going up or down? As x3 increases, is the function going up and down, right? Therefore, when we do this, when we take the derivative of a function of multiple inputs, then the output is also multiple. So it's the function with respect to x1. So you're only looking at x1 as the variable and everything else is a constant or x2 or x3 because you're holding everything constant and you're seeing that just this one particular input, if you were to increase this input, is the function going to go up or down? Okay, so this is called, we take the derivative with respect to one variable at a time. So x1, x2, x2, one variable at a time. And this makes a lot of sense because for each direction, for each input, we need to know if that particular input is pushing the function up or down at a given point. So so at this point, I've basically spent 10 minutes just talking about derivatives, right? So why so much emphasis on derivatives? Why do we care about them so much for machine learning and data science? Well, let's look at a quick example. So here, let's say we can measure three molecules from your blood, right? We don't know what these three molecules are, but the point is, after you measure these three molecules, we have identify a function. So when you plug these three molecules into the function gives us the probability of you getting cancer. Okay, so it predicts cancer likelihood, right? So, so that's what the function does. Now, assuming that we just measure your body, so your body, and then we measure these three markers, and we got our result back, and the results were 239. Okay, they don't really mean anything until you plug it into the function. So you plug 239, three inputs, into your function that takes three inputs, and out it spits 97%. So it's saying that you have 97% chance of getting cancer. Well, those are not very good odds, but okay. That's what I said. The function has a purpose. You put some input in and give you some predictive information. Now, now, let's say we plug these same numbers, 239, not into the function, but into the derivative of the function. You see this prime? The derivative of the function. So if you plug it into the derivative function, and now we get negative 0.001, negative 6, and 20. Okay? Now, given everything we talked about up till this point, take a moment and think about what the derivative just told us. Okay? Okay, if you want to pause the video and think about it. What did the derivative tell us in this given example? Now, given that you have three different drugs, okay, you have three different drugs, drug 1, 2, 3, and they can respectively increase the amount of blood serum X1, X2, X3. So you can either increase X1, you can increase X2, or increase X3. Well, which drug would you take if you want to lower the cancer rate, right? And which drug should you take if you're just trying to die? Okay, take another second and think about this. Okay. So from this previous derivative, remember the derivative is telling you that if you were to increase this value, x1, what's the probability going to behave? And right now it's saying that if we increase this factor, x1, the probability is going to reduce. Even though it's tiny, it's not reducing very much. But here, if you were to increase the second factor, you take the second drug, it's going to reduce the probability of getting cancer by 6 points. That's quite a bit. And then the third one, if you were to increase this factor, you're going to increase the probability of getting cancer by 20%. So obviously we don't want this, right? So this is probably some kind of carcinogen that's not good for you, and you don't want that. So you can see that knowing the probability, like knowing f of x, is useful because it predicts the probability of you getting cancer. But but knowing the derivative allows you to take action, concrete action that manipulates certain input to achieve a certain output, right? So right here, we want to lower the probability of you getting cancer. And the derivative essentially tells us how to achieve that. Okay. So machine learning, very often in data science, it's all about decision making, right? And the derivative tells us which way to go. Right? Without the derivative, we cannot tell if we want to increase the first factor, second factor, or the third factor. They're just inputs, right? So knowing the derivative is that important. And basically, 99% of machine learning is about manipulating the input to see if you achieve some kind of output. Right? There's this thing called gradient descent. You're essentially figuring out what input you should get that gives you the lowest output. So 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 I'm not. This is not hyperbole. That's how important derivatives are. So how can you really know how to do machine learning without taking derivatives? Well, the short answer is you can't. Like knowing how to do derivatives is really really important. But beyond just knowing how to do derivatives, like the basic derivatives is important, but like there are many other things that's important, right? Derivative is just the most fundamental thing. Like you really need to know basic calculus, right? If you don't know how to take derivatives, this whole class would essentially make no sense. It would be like taking a Shakespeare literature class and you don't even speak English. That's how important it is. However, beyond derivatives, there are many key topics that you guys would need to learn throughout the semester to really dig deeper into machine learning. Specifically, you want to know a little bit of Calc 1, 2, 3, linear algebra, probability, statistics, and programming. This is why machine learning is not like an easy topic. Like not only if you want to be very good at it, you need to master all these to really get the full picture, right? So here in Curry, we Curry really believes that machine learning is going to be the future, right? It's going to be the future. So we want a lot of students to be exposed to machine learning, even if they may not have all these. So this class is designed with that in mind. So in the beginning, we're kind of going to go over and cover these topics. After we cover these topics, obviously we're not going to learn everything, but you're going to learn just enough, the bare minimum, to allow you to kind of quickly catch up, and then that it allows you to like gain a deeper understanding of how like these machine learning techniques work. Okay. Now, first and foremost, you would like we would need to start with learning how to take derivatives. And essentially, we want to be able to look at a function, look at it, and then figure out what the derivative is. Okay? You have a function, and then cranks through your brain, BRAIN, and then outputs this. This is what we want to achieve. That we want your brain to output this when we input a function. Okay, so let's train your brain how to do this. And luckily, to get most of the what we want to achieve, there are only really 7 rules. I mean, obviously there are more than 7 rules, but these 7 covers majority of the bases and is good enough, at least for this class. All right. So like we're not going to cover everything. We're just going to do just enough. So that way we can do it quickly and you get the point. So let's start by doing the constant rule. Constant rule. A constant rule is when you have a function that is just a constant. So over here, a constant is a function that doesn't go up or down. So it doesn't matter what input you put. You could put 0. 0.2, 1, 1.4. You will always get the same value. And in this particular case, you're going to get 0. 0.2, right? 0. 0.2. So you're always going to get the same value. Now, the derivative of a constant value is very, very simple because remember, what does the derivative tell us? It tells us if the function is going up or down at a given point. Therefore, if the derivative is not, the function is not going up or down ever, then you just put a 0, right? So the derivative is always 0, which is very simple. So right here, the derivative of this is always 0. Right, here's some examples. So here you're taking a derivative of 3. This is just a constant value with respect to x, and therefore you're going to say the derivative is 0. Here's another example. The derivative of c when the variable is x. Now, remember, the variable is x, therefore anything that's not x is treated as a constant. And since this is a constant, well, the derivative is 0. Over here is x, but we're taking derivative with respect to y. So the y is a variable. Again, if anything that's not the variable is treated as a constant. Therefore, this is a constant. Once again, you got a 0. And over here, you're taking the derivative of with respect to x1. Therefore, x2, x3 are not x1. Therefore, they are treated as constant. Once again, they're all going to be 0. Okay, so that is the general idea of the constant rule. And if you just think about it visually, like the function is not going up or down, since the derivative tells you if the function is going up and down, then it has to be 0 because it's not going up or down. So that is the very first rule. The second rule is called the power rule. Okay, so the power rule is when we have a function of some variable. So here's x and here's x, right? To some kind of power. Hence the power rule. In the power rule, how do you find the derivative? Very, very simple. The rule goes like this. You take the power and multiply down. So you take the power and multiply. So since the power is 3, we multiply the whole thing by 3. And then you subtract the power by 1. Right? Then that's it. That's the derivative. Okay? So once again, you take the power, multiply down, and then subtract the power by 1. Subtract the power by 1. And that's it. Very, very simple. That is the power rule. Now, over here, there's several examples. So here's 3x, right? So let's say we want to take derivative. So 3x is, we can use the power rule because it's just x to the 1. Therefore, what we do is we multiply 1, and then we subtract 1 by 1. So that becomes 0. So this is just equal to 3, right? So that's how that works. Over here is a second example. We have 4. So we move 4 down. So we multiply by 4. And then 4 is going to subtract by 1. So 4 times 2 is 8. And then 4 minus 1 is 3. So that's the derivative. Here's another one. Now, y is the variable, okay? Therefore, x is a constant. What that means is you have y to the 1 and x. So what do? We multiply 1, xy, and then 1 minus 1. So this cancels out, which equals to x. So this cancels out. Okay? Over here is x1. Therefore, x2, x3 is a constant, right? Only x1. So this is just treated as a constant. Now, since this is a constant, we multiply 2 down, so 2 right here, and then 2 minus 1. So 2 times this here, and then 2 minus 1 is just equal to 1. So here's x1. So these are the examples of power rule. Okay, the next one is the sum rule. Right? If we have a function, so far we've done the constant, power, and now the sum. So sometimes we have combination of these. So we can solve this with the power rule. We can solve this with the power rule, and we can solve this as a power rule, and we can solve this as a constant rule. So individually, we just learn how to solve them. But once we add them together, how do we deal with this kind of problem? Well, it's very simple. You just solve each term individually. So you solve this one, you solve this one, you solve this one, and then you recombine them together. So here's plus, minus, minus, plus, minus, minus. You combine them back together. So power rule for this, let's see. So it's 3x. So this would be 3 and 3 minus 1. Power rule again, 2 goes down and 2 minus 1. Power rule again, so that's just equal to 1. And then over here is a constant, so that becomes 0. And then you just recombine them together, plus, minus, minus, plus, minus, minus. So once you combine them together, this right here is the result of the derivative, which is 3x squared plus 4x minus 1. Yeah, and this is 0, so we can ignore that. So this is the result. Over here, here are a couple examples. Right? So 5x and 3. So if you use the power rule here, that just becomes 5. This is a constant rule. That's 0. Over here is x1. Therefore, that is 0. So 2x1 and 1. So this right here, the idea is the same. You just solve each one of them separately using the power rule or the constant rule and recombine them together. Okay? So that right here is the sum rule. Here's a quick example. So over here is the green line that we've been working on throughout the class. So now we know how to take the derivative of this. The derivative is essentially the power rule here and the constant rule. So the power rule will be 2 times 0.3 x2 minus 1. So this becomes 0.66 x, right? That's the result we got. So we now know how to take the derivative of this very, very basic function. And this now allows us to plug, once we have this function, it allows us to plug any value in and figure out that at this point, is the function going up or is it going down? Okay? So that's how this works, right? All right, the next one is called a product rule. So product rule is when you have separate parts of a function that is multiplied together. Obviously, the easiest way with what we learn is we can multiply them out. So this becomes 4x cubed and 4x squared. If you actually multiply, right? You multiply them together, that's what you will get. And then we can use the sum rule to calculate derivative. So you could do that. However, there are times that you can do it better, or it's easier if you use the product rule. And the product rule is very simple. We essentially split the function into two portions. After we split the function into two functions, a and b, then the derivative with respect to x of a times b, right, a times b, is simply the derivative of a times the function of b, and the function of a times the derivative of b. So that is the product rule. Okay. So over here, let's say we take the derivative of a. So taking the derivative of this is 2. And then taking the derivative of this is 4x. So now, if we know the derivative of a and b, we can plug it into the product rule. Right? The derivative of this is the derivative of a times b, and then a times the derivative of b. So let's plug them in. Derivative of ax is 2. And then b, the function b, is 2x, right? That's b. And then we'll take the function of a, which is this, function of a, and then multiply by the derivative of b, which is 4x. Now, if we multiply all these out, we will get this result, which is identical to what we solved previously when we simply multiply them together and use the sum rule. And so the power rule, in many cases, will make your life easier. Okay? The product rule, sorry. I meant the product rule. Okay, so now let's try to use your knowledge of what you've learned so far and see if you can solve this, right? I would like you to use the product rule, right? Use the product rule to see if you can get the result. All right, pause the video, take a second, try to solve it yourself. You can refer back to previous portions, and when you're done, the solution is here. So you can take a quick look on whether you were able to achieve the product rule. Okay, pause the video and do this, and we're going to move on. Okay, so the next thing we're going to do are these things called exponential functions. So in mathematics, we have this thing called the pi, which is 3.1415, etc. But there's another magical number called e, which is approximately equal to this value, 2.718 something something. So these are like magical numbers that just exist in mathematics. And we often end up seeing exponential functions. An exponential function looks like this, where f of x is e to the x. Okay? E to the x. So it's to the power of x. And these functions we see often, and we also need to take derivative of these functions. Luckily, the derivative of these functions are really, really easy. It's simply itself. So if you take the derivative of e to the x, it's simply e to the x. So there's not much to remember there, right? You just need to know that's how exponential functions behave. Okay. All right. So those are exponential functions. Next, let's move on to logarithmic functions. Logarithmic functions, well, they, they look something like this, right? So log of some base, and then you plug x in. So this log is a logarithmic, and x is the value you plug into the function. So what does this really mean? Well, what this means is that this right here is equivalent to saying that 2 to the power of y is equal to x. And we're trying to find which power will give us x, right? And this right here is called a base. You can pick any base, any base. So you can pick base 2, you can even pick base e. In fact, base e is one of the most commonly used one. Okay, so this is the common, and what it's saying is e to the power of y is equal to x. Therefore, given e and given x, what power do you need to achieve this equivalence? So that's what like taking a log means, is which you're trying to find this power. Okay, so when the base happens to be e, right, instead of 2, then it has a special name called a natural log. And it's commonly written, instead of log, you write natural, like log n, so ln. So when we want to take the derivative of natural log, okay, ln, the derivative is quite simple as well. So over here, we want to take the derivative of the natural log. The result is 1 over x. Okay, this is something you would just have to remember. So taking the derivative with natural log is easy. But what if you don't have a natural log? What if you have log base 2? Well, to do this, we simply have to convert these logs into natural logs. And the way it works is such. We have, for example, log of 2. There's a very special property for logs to convert into natural log, which log of 2 is equal to the natural log of x divided by natural log of the base. So if you have 4 here, it would be natural log of x times natural log of the base. And once we have that, natural log of 4, natural log of x, if we want to take the derivative, this is just a constant. We can ignore that. We can like not ignore, but we don't need to pay attention to this. We only need to take the derivative of this. So over here, this is equivalent to taking the derivative of the natural log of x and natural log of 2. And we can move the natural log of 2 and move the derivative inside. So notice how the derivative is only taking this, the natural log of x. So the derivative of this, we just learned, is 1 over x. Therefore, this is 1 over x times 1 divided by natural log of 2. So now this means you know how to take the derivative of natural log of x, and you know how to take derivative of any log base of x. Okay? If it's not natural log, you simply have to convert it first into natural log. Okay? All right. Our final rule of the day is called the chain rule. Final rule is called the chain rule. Chain rule allows us to take derivatives of really complex functions. Like it, what it does is it really simplifies the function for you. So over here, let's say we are trying to take the derivative of this, right? How will we go about doing this? Well, we can do this by simplifying this into simpler and simple functions. So over here, we want to take the derivative with respect to x. All right. And notice over here, we can simply pack that together into a separate function. And I'm going to call this function g, right? So that's g. So what that means, if this is g, then f of x is equal to g to the fourth, right? Okay, once we have it simplified in this form, it's quite easy to find the derivative with respect to g, not with respect to x, right? So if you want to find the derivative with respect to g, we simply have to use the power rule. So you move the 4 down and subtract by 1. That's how we get this. So we now know the derivative of the function with respect to g. And g is also a function, right? We just said g is a function. And therefore, we can also take the derivative of g with respect to x. So this is g. So what if we take the derivative of g with respect to x? Well, that's also pretty easy to solve. This right here is just using the power rule. This is just equal to 2. Okay, so notice that if we have df dg from here, and we have dg dx. So what happens when we multiply the results here and the results here together? Well, if you have df dg dg dx, notice dg dg cancels each other out, resulting in df dx. So all we have to do is multiply them together. So over here, we have df dg right here, and then dg dx here. And then when we multiply, 2 times 4 is equal to 8. So the result is 8g to the cube. Well, what was g? Well, we said g is this, so g is 2x. So the final result tells us that we can take the derivative of this by really simplifying it. And this idea like really chains itself. It's called a chain rule for a reason, because we can bundle very complicated variables. So if it's more complicated than this, you can do this over and over again. So for example, you can have df dx, no, dg, dg, dq, dq, dx. Right? So you're basically packaging. Notice how dg cancels out, dq cancels out, resulting in df dx. So you can keep chaining more and more complicated equations, making them into simpler ones, and then you multiply them together in the end. And that is the general idea of chain rule. Okay, so like we went through quite a bit pretty quickly, and it's you can't just get this instantly unless you already know it. If you don't know this, you need to essentially practice a couple times and get your reps in. Okay? So let's now try to solve this. Okay? I want you to pause the video, use everything we've learned so far. Like this one requires you to use the chain rule, right? Here's the exponential function. So make sure you can do this. Okay. All right. Ready? All right. We can move on. Okay. I'm gonna move on. Now to solve this right here, remember this right here is natural log of 2x squared and then natural log of 3. This right here, we can just copy it. 2x e to the 3x. Actually, no. Let's solve them one at a time. So, do we know how to solve this? Well, this is equal to d dx, right? This is equal to 1 over log of 3 d dx log of 2x squared. Okay, now let's call this whole thing, let's call this thing g. So therefore, it's just log of g. Log of g. So g is equal to 2x squared. Well, if that's the case, taking a derivative with respect to g is pretty easy. So log of 3 d dg is just 1 over g, right? So it'd be 1 over g. So this right here is df dg. Now let's find out dg dx. dg dx is therefore equal to, well, use the power rule, is 4x. So now if you want df dx is equal to 1 over log of 3, 1 over g, 1 over 2x squared times, so that's this. Now we have the times 4x. So the result is 4x 2x squared log of 3. So that's 2x natural log of 3. Okay. Hopefully you were able to get this. So that's the first part. Remember, we got to do them separately. So the very first term, if we take the derivative, it will give us this. Now, if we try to solve the second one, let's see if we can solve the second one. So I'm gonna ignore the negative sign. Okay, we'll put the negative sign back later. So 2x e to the 3x. Okay, this is harder. So this, what we could do is use the product rule. So we take the product, the derivative of this, which is 2, times this. So this is a, right? Ax, bx. So derivative of a times e to the 3x. And then plus the derivative of this. So derivative of this is, so what is the derivative of 3x? Well, this is b of x is equal to this. Well, we can call this part c. So b of c is equal to the e to the c. Now the derivative of this is easy. So db dc is equal to e to the c. Now dc dx is equal to, well, we take the derivative of this with respect to x, so it's 3. So now we multiply them together from the product rule. Then it's e to the c, which is 3x times 3. Okay, 3 e to the 3x. Okay, so that, and then the negative is over here. So that's the derivative of the second term, and this is a constant value, right? So that's basically it. Hopefully you were able to do this. Did I do this right? Oh, there's a 2. Yes, I missed something. So this right here has to multiply by 2x. Okay, 1 second. Let's do this again. So I think I messed it up slightly. So I think I forgot to multiply them. Okay, so one more time. 2x e to the 3x. So this right here is a of x, and this right is b of x. So that's from the product rule. So we take the derivative of this one. So it's 2 e to the 3x plus, we take the derivative of this. We did that previously, which is e to the 3x times 3, and then multiply by 2x. There we go. So therefore 2 e to the 3x plus 6x e to the 3x. Okay, and then there's a minus. So that's the derivative of the second part. So in the end, you should get this solution here, okay? Which I think it is correct. Yes, it is correct. Okay. So that is how we use the product rule and everything. Now, we just learned how to take derivatives, and I was able to show you the answer. But when you go out in the real world, answers aren't provided for you. Very often, you don't have the answer. You just have a function. Your boss tells you to find a derivative and solve it, and you can do it. But how do you make sure? How do you know that you're correct? Okay, so if you are in the real world, you need a way to double check your work. And the way you can do it, I'm teaching you now, is to use Python. So these are the libraries you will need to use. So we just calculated. This was the derivative, right? And let's assume you don't know that this is the right answer or not. What you can do is in Python, you can define a function. This function is the function we're trying to take the derivative of, right? This is that function. So you define the function, and then you define the derivative which you found. So you found this. You found this. So you have both. Okay. Now, the key function here is called grad. Grad. Notice we pass the function in here, and we get another function called autograd. This is the automatic discovery of derivatives. Okay, so this function right here, if you plug any x in, it should give you the derivative at that point. So, well, it doesn't tell you the function, but it tells you if you plug some x in, what the result is. So what you can do is you can just randomly generate a bunch of numbers and then compare the result of your derivative, right? This is the derivative that you found with the derivative according to Python, right? And therefore, the output should be identical. This is the automatic derivative finder, and this is your theoretical result where you found the equation. And if you did a good job finding the derivative, the automatic derivative function and your derivative should output the same output given the same input, right? So I randomly generated x. I put them into auto-generated versus my, and the fact that they are able to achieve the same result confirms that the function I found is pretty good. It's pretty good. Okay, so this is one way. There are other ways to confirm your derivative. This is a very very simple way. Now, one thing I want you to notice is that in Python, when they used log, L-O-G, they mean natural log. I don't know why they do it that way. I would prefer if they use log, natural log, but that's what they mean when they use log. That's just a quick aside. Okay, so okay. Now that we've done the derivatives, you can do derivative. It goes from f to find the derivative of x. Okay, and let's call this f of x. What happens if you do the backwards of a derivative? We know that if you take the derivative, it tells us whether the function is going up or down. What happens if we do backwards? Well, when we go backwards, something very special happens. Right? I'm gonna denote. Um, it turns out that when you go backwards, the function allows us to find the area. So, like, let's say over here, this is just an equation of a line. Okay, given this equation of a line, what if you want to find the area between 2 points? So over here is A and B, right? You want to find the area between A and B. So essentially this chunk. What is the area here? Well, this right here is 1 times 4. So the area is a 1. No, this is 2. 2 times 4. So 2 times 4. The area of triangle is therefore 4. So we know the area here is 4. But, how do we do it using calculus? The way we do it is that we write the equation of a line like such. So this is how we mathematically represent it. So that's 2x. That was the one we were just looking at. And then we denote the range between a and b using the integral sign. So a and b. And what this is telling us is that we want to find the area under the curve between the point A and B. That's what it's saying. That's what this symbolically means. And over here, A is 0, right? B is 2. So that's what we're trying to find. This process of solving the area under the curve is called integration. And the result of solving this equation and finding the area is that we're finding the integral. Okay? Since we know this is a triangle, we know the answer is 4. But let's see if we can reproduce this using calculus. Okay? So, remember what I told you. This is the function, right? This function is f2. And we can picture the antiderivative. You're doing the backwards of derivative as the function f. So we're saying that there's some function f that if you take the derivative, then we're going to get 2x. Now, remember, previously we have f, and we take the derivative, d dx, we find the derivative. But now we have this thing, we call that f of x, and we're trying to find the original derivative. So we're going backwards. So if we just do it backwards, then we're trying to find like this function, capital F. So what capital F, after we take the derivative, will give us this. Okay? So we would need to take the derivative backwards. And if you were to think like the process backwards, you will notice that if we f of x is equal to x squared, right? Take a second. See, if you use the power rule and take the derivative here, what would it be? Well, it'll be 2x, right? So if we found a function such that if we take the derivative, it will give us the original function back. Okay? So now we know that if we take the derivative with respect to x squared, it will give us 2x, which is what we need, and therefore the antiderivative, the opposite of derivative, is x squared. Once we know this function, the area between a and b is simply you plug f of 2 minus f of 0. All right, so you plug whatever the top limit is, which is 2, and then the bottom limit. If you were to subtract them together, that gives you the area under the curve. So what if we plug first one, f of 2, right, capital F of 2, which is equal to 2 squared, and then we plug 0 in, which is equal to 0, the result is 4. Remember, we knew the area was 4 already. Over here, we simply calculated, instead of using geometry of calculating the area of a triangle, what we did is we use this concept of antiderivative, like doing derivative backwards. And that also allows us to find the area. Okay? So the key takeaway here is that given function f, the derivative, if we were to take the derivative of this, then it tells us if the function is going up or down. Like we spend most of the class talking about derivatives, and that's what it tells us. Now, if we were to do the integral, which is the opposite of derivatives between 2 points, it tells us the area under the function between these 2 points. Okay? Okay. Now, to take integral, there's also a simple way. What we can do is we define the function. Remember, here's the function. And then we can use this function called the quad. When you use the function quad, you take quad, the function between 0 and 2. It tells us the area is 4. Okay, so you can solve this integral using antiderivative, and you can confirm your result using Python to see whether you get the same result. Okay, so now let's consolidate everything we've learned by doing these examples. So what I want you to do is solve each one of these, the derivative and the antiderivative, by hand. And then I want you to pull out Python and see if you can confirm your own result, like whether what you coded in Python is equivalent. Okay, and hopefully they're the same. And that's it for today. If you're interested in extra tutorial on derivatives, you can look at this video here. So okay, all set.